Hello everyone, my name is Sergio Sevillano. Thank you very much for watching my talk. I'm a postdoctoral researcher at Durham University, specifically in the Institute of Particle Phenomenology. And before that, I was in Nottingham, where I specialized doing modified theories of gravity. So because I've moved from modified theories of gravity to kind of particle phenomenology, today I'm going to be talking about a recent paper that I published that basically combined the best or maybe the worst of both worlds. This paper that I'm talking about is a particle's perspective on screening mechanisms. And what I try to do here is trying to study whether particle physics can say anything about modified gravity, specifically about screening mechanisms. But before that, let's try to kind of introduce why we are modifying gravity here. So we know what gravity is. It looks like that. And this is the Einstein-Hilbert action is called. And this gives us everything we know about general relativity. But it's important to say that this is not just general relativity. This is a specific model inside general relativity. General relativity is something much wider that we can kind of modify and still be consistent with all the symmetries that we know and love. In this case, there are many reasons why we could modify gravity. One of them is that we know that it doesn't really work. The story is not complete, and there must be something else in order to explain all the different problems that we find in nature right now. So some of these problems can be, for example, the cosmological constant problem, dark matter, the early universe, so for example, inflation, and whether there are phase transitions, or all these problems over here that like the coincidence problem, Hubble tension, strong. Well, there are so many that you can see that they go behind Einstein's picture. And yeah, you can pick one of these problems and dedicate your whole life to one of these problems. But normally what people do is take the standard model and take one of these extensions of the standard model that go into the beyond the standard model theories. So for example, some of these extensions is adding WIMPs or the axion or the inflaton or some field, a scalar field that leads to quintessence. And this is very much accepted, and it has been very well constrained because we have the LHC and we can test for these theories. However, we can take a different route. Instead of modifying the standard model or the matter sector, what we can do is modify the gravitational sector in the same way by putting new interactions in it. That would mean that we are going from some standard Einstein-Hilbert action to a new type of action that is what we call normally modified gravity. There are many ways we can do these modifications. However, for time purposes, I'm going to just go directly to the model that I'm going to be studying. That is the simplest one. This is a scalar-tensor theory. In particular, is the Brans-Dicke theory. This is the simplest you can imagine. Here we have just a new scalar field. You can see that this is the kinetic energy and this is the potential energy. Here we have some matter action that I'm not defining yet, but this would be kind of like the standard model, for example. And we have this new coupling between the scalar field and the Ricci scalar. These type of couplings are called non-minimal couplings, and they will lead to very crazy new dynamics that we are going to explore here. But the main thing that you can tell already is that we know something about this phi field, because we know that here in standard gravity we have the Planck mass squared. So basically we need the field to find a vacuum expectation value. This is the V, the VEV. And whenever we evaluate f of phi on this vacuum expectation value, we should recover m Planck squared, so that everything is consistent with the normal theory that we know of gravity. Well, because we are modifying gravity, we will expect new phenomenology to come along. And the main phenomenology that we find in this type of theories are called field forces. These are long-range forces that will look like kind of gravity, and well, they may break, for example, the equivalence principle, but in the end what we will find is that some forces do not look like gravity, and so it will mean that there is a new theory of gravity. We find that normally this is, for example, the new potential that we can see constrained in this plot. This is not mine, it's by these people. And the first term, the one, is basically the Newtonian potential that we already know of. And this new term would be the field forces. Here, alpha is nothing but a strength coupling, like it will modulate the strength of this new coupling, and lambda is related to the mass of this field. It actually is the inverse. So the heavier is the field, the more suppressed is the field forces. And you can see that we have a lot of constraint on this parameter space. However, there is something very kind of funny about modified theories of gravity and scalar-tensor theories in particular, and that is called screening mechanisms. What screening mechanisms do is take advantage of this new coupling between gravity and matter, and between gravity and the scalar field. Now, because gravity is coupled to the scalar field from one side, and from the other side gravity is coupled to matter, there is a way of kind of making an effective coupling between gravity and the scalar field through gravity. And what happens in the end is that we are going to find that there is always an effective potential for this scalar field that depends on the local density. So normally we would have just this term, and that would be the whole story. But because now the field couples to gravity and gravity couples to matter, we are going to have an effective coupling between this field and matter. And so this means that we will have an effective potential that depends on the background. And what screening mechanisms do is trying to use this new thing to avoid any type of field forces or constraints that we already have on field forces. For example, the chameleon model, what it does is to take the mass of the field and make it very, very heavy. So if your free theory would live here, suddenly what you find is that when you have high densities, like the ones we live in and we make experiments, what is going to happen is that the field goes from being at this point to being moved to that point, because now it's heavier and we cannot constrain it. While the symmetron, what it does is, instead of changing what is the mass of the particle, what it's going to do is changing what is the strength interaction of the field forces. So that if your field lives around here, what is going to happen is that it pushes it down there. So these are two mechanisms, among others, that can show how screening mechanisms and local couplings to matter will change the properties of modified gravity. Now, normally there is like kind of a paradox that you can find here, that it could be the case that every time we are making an experiment and building an experiment up, the own experiment is screening the field forces away. So is the experiment itself the one that is hiding these field forces? So what people normally do today is trying to find new phenomenological implications that do not depend on screening mechanisms. However, what I want to show here is that there is a way of actually using screening mechanisms in our favor, because particle physics will be very sensitive to these screening mechanisms, and I will show you now how. So the first thing is how to work with particle physics in modified gravity. Well, the main thing is that it's super difficult normally, so you should avoid it. But there is one trick to do it and make our lives easier. There is always, using field theory, a transformation that we can make so that modified theories of gravity with a standard model will always look as general relativity with beyond the standard model interactions. Once we have beyond the standard model interactions, we can forget about general relativity and calculate everything we are looking for just doing standard QFT calculations. So let me show you how this works. Imagine that we are working with this branch-Dickey action that I showed you before, where again we have the field, the potential, the non-minimal coupling, and some matter action. Well, the first thing that we can do, that is really simple, is taking this transformation of the metric. Now, because we are choosing these couplings very carefully, what these couplings are going to do is basically transform the Ricci scalar in such a way that this function will disappear. And so here we will have a constant, and because now we have a constant, this will look as the Einstein-Hilbert action that we know and love. However, because we've made this transformation, now we find that every time we have a metric inside the matter Lagrangian, we will now generate these couplings, and these couplings are the one that will generate this beyond the standard model-like theory. Let's look at this with an example. Say that we have in the Jordan frame, the one that I was showing before, it's called frames, depending on where are you living, like if you take the conformal transformation or not. We have a photon, and we have the Higgs, and we have a fermion. So basically this is kind of like a QED plus Higgs singlet model where you have interactions. This term over here is nothing but kind of like the covariant derivative for the fermion being expanded. This is the spin connection, if you know about it. And this over here is just the coupling between fermions and the photon. Now we have here the coupling between the fermions and the Higgs. So the Higgs, now I'm calling it just phi. And because we have this coupling over here, what happens is that when the Higgs finds a Bev, now we're going to have this effective mass for the fermion that is being generated because of the Bev of the Higgs. Now, when we make this conformal transformation, I'm going to skip some steps for time. What we find is that we can make even more transformations here so that everything is canonically normalized. But in the end, when we make all the transformations needed, what you find is that now we have this chi field that is basically being redefined so that you can see that so that is canonically normalized, but chi is basically the same thing as phi. Now I'm calling, instead of talking about F's and Planck mass, I'm just going to be talking about A of chi's that has all the information about the field forces. But the important thing is that you see that there is a standard theory of gravity now, so we can forget about this. And what we find is that the photon is not being modified because it's conformally invariant and we have made a conformal transformation. Now, the fermion has lost all these interactions also, but the Higgs now has these interactions appearing on the potential and on the kinetic sector. This one, we can forget about it most times because it's very suppressed, but this one over here is going to be very important. And normally, these interactions through the Higgs are the ones leading to the field forces. But I'm not going to be focusing on field forces in this paper. You can actually read this one if you want to look at the field forces and how they get generated. What I'm interested at is at looking at what happens when we find the vacuum expectation values on this theory. So this is based on a previous paper when they took A of chi equals to 1. This paper is by Claire Burrage and Pete Millington. And I'm not going to do that. Why? Because when you take this approximation, you find a solution that actually is kind of misleading, or at least is not as complete as you can make it. So I'm not going to take this as an approximation of assuming that this function is going to be equal to 1. I want to see what happens when you allow this function to actually vary with the space. And there is new term here that this is the effective coupling of the Higgs to the, well, it's not an effective, it's the coupling of the Higgs to the local, well, to the number of fermions that you have in the theory. In a way, you can just take some statistical average of what is this, the number of particles that you have, and this is related to the local density of your theory. So when we find the equations of motion of this theory, so that we can find the vacuum expectation values, we see that this theory is leading to, this term is leading to the normal equation for the Higgs, but now we have one more term for the local density, and this term is the vacuum expectation value for the chi field that is coupled through to the Higgs through these waves. But here we don't have any density dependence directly. When we solve these equations, we actually find these two equations over here. That is the standard ones that we always study, which is really nice because we have found a new way of explaining why screening mechanisms arise. You can see that, well, this term is kind of always suppressed. That's why we never find rho dependence on the Higgs, sorry. And these two terms over here are going to be modifying what the value of the Higgs is doing. We have this constant term, that is the one from the standard model, given by that fraction over there. And now it's being multiplied by this A of chi function. And when we look at what A of chi is doing, is actually given by this equation of motion for B of chi. And we have the standard potential, but now we have this effective new coupling, creating an effective potential that depends on the local density. So we are recovering exactly what we are looking for. The characteristics and properties of chi will depend on the density of the background. And you can see something very interesting here, because now, normally we don't have in the standard model, we don't have this coupling, right? If chi didn't exist, we would just have this constant term over there, right? So normally we find that in the standard model, the local density is decoupled from the standard model. However, because now we have added this new field into the system, we find that the local density is going to effectively couple to the standard model through this chi field. So now we go that we have the local density will affect chi, and because this depends on A of chi, it's going to affect the value of the Higgs. And what is the value of the Higgs? Well, the value of the Higgs is related to the mass of elementary particles, which is great because now what we are finding is that actually every time we are changing the local density, this is going to have a direct effect on the mass of fermions, and this effect can be measured. Because this is basically nothing but screening mechanisms, this is the equation from the screening mechanisms, you're seeing that every time we have screening mechanisms to hide the field forces away, we will find that the mass of elementary particles is going to change. And something really cool is that this is not something new, this is actually physical, and this was studied in terms of time. So when the field is rolling down its potential in cosmological times, people have studied that this will impact the mass of the particles. However, the thing that I'm changing here is just assuming that today, because we are going to be changing what is the vacuum expectation value of this particle, depending on where you are in space because of the local density, we find that this is not something that only happens in time, but also in space. And we can use it to constrain this type of theories. For example, let me show you two theories. Here is the chameleon that I was talking about on the symmetron. The chameleon, if you remember, is changing the mass of the propagator. So you can see that the potential here is just an exponential, so it's this black line, and A of chi is another exponential, that is going up. So instead of for the field to just roll down and down and down, what happens is that now we have these two functions in the effective potential there that are creating a new effective potential that is these U-shaped potentials. So actually, the more you are putting the more density you put in the system, basically the only thing that is happening is that you're squeezing the field more and more, and that is increasing the mass of the field. And it's very interesting because you can see now that depending on where you are and what is the background density, the field is going to take different values in the potential. And because that is related to the mass of the field of the standard model particles, we will be able to measure that. Similarly, here we can have the symmetron case that basically has a double wall potential and a quadratic. You can see that this field, the only thing that is doing is, if you don't have any density, you fall into one of these two degenerate vacua. But when you have a lot of density, this function becomes relevant. You pick up kind of the quadratic and you restore the symmetry. So now the field will lie over there. What is the effect that this has on particles? Well, if you just substitute for the vacuum expectation values, of course you will have to make a better simulation for this, but like as a naive calculation, you can see that for the chameleon, what happens is that depending on what values you use, the effect is going to be always kind of exponential, well, logarithmic. So that's why it's here it looks like a straight line, but this is a log-log plot. And you can see that it's very, very sensitive. You could say that this is kind of over screen. So say that I'm trying to put more and more density into the system so that there are no field forces. We will be able to really tell apart what is going on by the particles' masses, because it's related to A of chi, as you can see. This is the electron mass, for example. While in here, what you have is that because you go from one degenerate vacua to the restored symmetry point, there are only 2 points where you can kind of two stable points. And depending on where you lie, you're going to be in one point or the other. And by changing the parameters, what you're going to change is where this threshold density will be at, or how much is the rescaling of mass that you can find. So basically, this is something that you can measure. You can see that the densities in the universe are very, very inhomogeneous, up to the point that you can find in the critical, this is not the vacuum, this is the critical density of the universe today. So actually the vacuum should be even less dense than that. You will find that you have even 30 orders of magnitude of difference. So this is something that you can test for. Every time you will have a system emitting light at some point, you can see what is the, you can constrain the mass of the electrons at those points, and by constraining what is the mass of the electrons at those points, depending on what the radiation is emitting, basically you will be able to constrain modified theories of gravity, because they predict in screening mechanism sectors, they predict the mass of elementary particles to be changing in space. So thank you very much for your attention. I hope you enjoyed the talk, and I will be happy to discuss this with you in the discussion session, and hope to see you there. Goodbye.